Hello and welcome to the Math Studio. In this video, we're going to have a brief discussion on the limit definition of the derivative. And it's actually based upon this fundamental problem here. What is the gradient of the tangent to the curve y equals function x at point P? So here's our diagram, here's our y equals function x. Okay, so it's just an arbitrary function, doesn't resemble anything necessarily. Okay, here's our point P. Okay, and it's got coordinates x comma f of x, and that sits on the curve. Our red line here represents our tangent, so that touches the curve at just one point, obviously at point P. Now our blue line here is secant AP, and I'll talk about that shortly. So back to our fundamental problem. We want the gradient of the tangent, but we only have one known point. In order to be able to work out the gradient of a line, we need 2 points, don't we? So this is our y2 minus y1 over x2 minus x1. So it's sort of our 2-point gradient formula. Okay, but what do we do about this? We've only got 1 point. So in order to be able to at least come up with an estimate of the gradient of the tangent at P, we need to use a second point somewhere. So let's say we chose another point. So let's say we chose point A, a little bit further along on the curve. Now point A is a little bit further along than point P in terms of horizontally. So if point P has an x coordinate of x, we're going to move h units along. Point A will have an x coordinate of x plus h, so h units sort of along. The y coordinate of point A will be f of x plus h. So in other words, substituting x plus h into whatever function we have, that'll give us our y value. Now we have 2 points. We can at least estimate the gradient of the tangent at point P by just using this point A and point P and using the 2-point formula for gradient. So the gradient of the tangent at P is approximately equal to the gradient of secant AP, provided we chose point A not too far away from point P, of course. Now, I'm going to write this using the proper notation. F dash of x, that just represents our tangent, or the gradient of our tangent. This red line here. So this is f dash or f prime. So f dash of x is approximately equal to f of x plus h minus f of x over x plus h minus x. So that's y2 minus y1 over x2 minus x1. Now, of course, the x plus h minus x, the x's cancel. Okay, so we can cross those off. And we end up with f dash of x is approximately equal to f of x plus h minus f of x over h. Now, how do we make the estimate of the gradient of the tangent at point P more accurate? And it's pretty clear that we need to move point A closer and closer to point P. So how do we achieve that? Remember that point A is h units away from point P, at least horizontally. So if we make h smaller, in other words, we're bringing point A closer and closer to point P, the blue line, at least the gradient of the blue line, begins to approach the gradient of the red line, the tangent. So, and I've written this here. So now the gradient of secant AP approaches the gradient of the tangent at P as h approaches 0. Okay, we have another fundamental issue that now comes up. What happens if you make h 0 here? Well, you've got a run of 0, and that creates a problem in itself. You can't have division by 0. So therefore, we have this operator, this limit operator, that'll sort of help us in this process. Now, if we can somehow make h 0, then the secant, or the gradient of the secant, equals the gradient of the tangent. That's no longer an estimate. So f dash of x is in fact equal to, no longer approximately equal to, but equal to the limit. So think of the limit as like an endpoint, sort of an end value. The limit as h approaches 0 of f of x plus h minus f of x, so that's our rise, so y2 minus y1, over our run of h. In subsequent videos, I will look at examples of this, so thank you very much for watching and wishing you all the best for your studies.